All right, so that was a little bit of a deep dive into how we do the editor. Because, yeah, in a way, Makepad was originally designed to be able to do an IDE in. What is it? I think do I have image? Yeah, okay, so one of the main architectural constraints of Makepad was that we're able to draw an editor with code folding, right? We are able to generate this quickly enough that you can make editors that actually push the boundary, right? So we want inline AI assist, we want inline widgets, we want zooming, we want all these things that are very difficult to do with an HTML structure. So Eddie, I think, gave a good idea of how to layer an editor on top of Makepad. Yeah, because it's a cornerstone of of what we built, and also one of the primary performance benchmarks that I had originally is like, after Cloud9, can I build an IDE that has performance? So one of the building blocks of getting that performance on the CPU side, right? Because if I fold this, this animation is running on the CPU side, right? It is relayouting the text in the code editor, and it's doing it fast enough that I can do like 60,000 characters or something in a view, and it's not a problem. So how do you get that performance? Especially also running on web, right? And the way to do that is you make the data path from the CPU to the GPU very narrow, very simple. You use instancing. So to illustrate that, I wanted to show you the piano keyboard here. I'm sorry that it's a little bit small. But the piano keyboard is a nice example of an instanced widget, right? The piano keys are instanced. They have it's a rectangle, essentially. Let me see if I can open that. Audiograph, widgets, piano. Here we have the piano. So if we put a return blue, let's see, hold on. Oh, did I break it? Oh, right. As I said, if you break the parser, then it needs to restart it. So this is the piano keyboard, right? If I return red, you see the whole thing is red. So how does this work? How do you draw things? How do you style things with shaders? So in order to hold on, I need to make it bigger. In order to do this, we made an API that runs on the GPU. So anything that you see here in the pixel function and in these other two functions is transpiled to a GPU language, like WebGL, it's using GLSL, or MetalSL on Apple, or HLSL on DirectX on Windows, and we hope to add Vulkan SPIRV or SPIRV, or however you pronounce that, to this as well. So you should see this as a kind of a new GPU language that looks a bit more like Rust than GLSL. But semantically, if you look at what it does, it cannot be much different than GLSL because it's transpiled. So you have to really think in the things you can do in this language is very similar to what you could do in a shader toy or in GLSL. However, I've added a bunch of features. So one of the features is that we have structs with methods, which is nice in Rust. So we can make an SDF2D struct that is a signed distance field two-dimensional object. It's an API that allows you to use two-dimensional signed distance fields to draw objects. In this case, we check if it's a black key or a white key, and we change the function that we call. So in this case, we use a box. A box is really just a rounded rectangle. That's the name we chose for the API. It's a rounded rectangle. Let's remove the red. So here we see the white key. So right, this is the roundness of the corner of the key, right? So this just fills the roundness. And in this case, when you press the key, as you can hear, we have audio. I don't have audio on the jack, so. It's really a fun toy. You should try it out. You can run it on the web, but you can also run it locally. It's quite a full-featured synthesizer. It's a sequencer. Yeah, it's a really fun toy. It's made by a friend of mine who runs a synthesizer company called This Is Not Rocket Science. Yeah, he built the synthesizer. We built the UI together with him as a test case of how can we build UIs like this. You know, it's just a very simple, straightforward UI in that sense. Yeah, we have this switch. We choose what type of key we have, and then in the white key area, you see that there's a blend function of a certain amount of colors, right? So let's see if I can hover. Right. So if I make this one red, I always like to use red as the test color. So now you see that the hover color becomes red, right? These values, hover, pressed, they are passed in from the CPU, right? So if you look at the piano key, you have the piano key is the Rust representation of the instance of a single key, right? And a single key has states, has animation states. It has a hover, it has a focus, it has pressed. And when you, in this case, you can write animation timelines that animate these properties. So we can animate the hover property, or we can animate the focus property. And you set this from code. So in the piano, I think, let me scroll here, when you do a finger down, or that's the API for using fingers, which is a unification of both touch and mouse inputs, so you don't have to write it once for both mouse and touch. In this case, when you press down with your finger, it says hover on and pressed on. And those two states then get passed into the shader via this value, hover and pressed. So when you see mix color A, color B with self.hover, it means that hover is a value that animates from 0 to 1, and it will transition, it will blend these colors from A to B. It's just a linear interpolation of two colors based on a value. So that gives you a hover color, right? If you animate a value from 0 to 1 with hover, you have a hover. So this is essentially the core primitive of how you style UI with shaders. You input animation curves on single values, and then you use those single values to write little programs to style it. And in this case, as you can see, the black key is actually very, I wish I should make this bigger. Let me see if I can make it bigger now. So this is not a CSS gradient. This is actually a little light that moves over the key and moves away again. And the way I did it is by writing a little, you write a dot product to compute the angle, or the how much light is hitting the object, and then you use that value to essentially change a color. It's that simple. However, this is something you can absolutely not write in CSS, right? You cannot write a little program that styles things with light computations. This is what shaders are originally designed for in computer games. Computer games use shader programs to compute reflections of light, of colors. That's why it's called a shader. It shades objects. They use it to shade objects. So here we can use it to shade UI. So when you see this light, let's see if I can change some values to make it do different things. Right, I'm now moving the direction of the of the light over the piano. As you can see, it changes color. I think maybe it's hard to see on the screen. Doesn't matter. The point is, you don't have to express your UI styles as a gradient. You can write little programs. And we've done a lot of work on making these programs composable. So they are inheritable, right? I want to quickly show that as well. Like in this editor, I'm sorry for picking these little minute things, but these are actually the things that are hard to do in other UI frameworks, where you have little teeny tiny details that you want to animate. Like you want to, when you press this plus or minus, you want the plus to be built up as it expands, right? You want a little animation that is built out of little tiny drawing commands. And the only way to do that in HTML is to use little canvas elements everywhere, and that just doesn't scale. So here we can write little programs that run on the GPU and have absolutely zero impact on the CPU. All we do is change one floating point value from 0 to 1 to animate that little plus, or to animate this thing from pause to play. But how do these shaders compose, right? How do they compose? Because if you have a text shader, in this case, you have the underline of the parentheses here that draw a little bar underneath the text, right? And in this case, I've implemented that actually as a subclass of the text shader, and I'll show you that very quickly. So we have code editor. Right, so you can put these little shader programs anywhere in your UI inheritance, right? I said earlier on that you compose UI components by doing straight line inheritance. So you have a button, and you can inherit my button from button and override properties, and then you can keep inheriting and modifying these values. It's a little bit like CSS, but you use only a single, a single selector per inheritance step. So here we have the shader for draw text. Right, drawing text is actually a fairly complicated shader. I'll show you the base shader. The base shaders are in Draw. The base shaders are in Draw, in Shader, Draw, Source, Shader. Here you find the base classes for all of our shaders. So we have one that draws a single color, very basic. We have one that draws icons, one that draws text, and one that draws a quad, just a square with no color. Essentially, you have to provide the program to draw the square. So, so when you go to draw text, you see that this is a fairly involved shader, right? It has a bunch of stuff in the geometry side, and well, actually I removed a bunch of stuff. It's not as involved as it used to be. It's going to get more involved again soon, because this is too basic, and you can see it, but if you do the zooming, the pixels are not great yet on the font. We're looking to improve this to an STF renderer. But either way, this is the pixel function, and you have to look something up in a texture. You have to use a power curve, and then you have to blend the color. And what I've done is this function here, blend color, does nothing in the default implementation, right? It just returns the color that you pass in. But if you subclass this one, you can override that little blend function, right? So here you can say, all right, draw text, override this blend function with something that does actually do something. So here, now I can change anything in the text renderer on the GPU based on hovers or colors or inputs, and modify the behavior of the text rendering. And in this case, what I do is the outline value. This is actually a class, so let's see. Makepad has a couple of ways of passing data into the GPU, and I think the most efficient one is by generating a draw struct. Here you say draw code text. This is the struct that contains the drawing information that goes to the GPU. Inherit this from draw text, that is the one I just showed you, the base class, but add this one property called outline that I can set between 0 and 1, right? So now, from Rust, I can actually set this value directly. I don't have to look it up into some table of the GPU compiler. I don't have to map it in any other way. Then I can set it directly from Rust and read it directly on on the GPU with self.outline, right? So here you go, oh, if we, in floating point, you should always use like large offsets, so don't compare, don't do equals 0, that is always a bit iffy, especially on mobile GPUs it can be a problem. So you just do like, if it's smaller than 0.5, that means that it's 0. And otherwise it draws a little rectangle if the Y position is smaller than whatever number you put in. So here we have underlines in the editor. And as you can see, this requires no other vector engine to be online or other complex CPU-heavy rendering systems to be present. You can just poke it straight at the GPU and it shows a little underlines. Now, of course, I don't like the underlines. They're in the way of the character, and I'm going to do it differently. But I do think it illustrates a point that you can customize the rendering very efficiently. Oh, you get to see the whole slide deck again. There we go. Where were we? Deep dive. Yeah, so shader inheritance we did. So a little bit more on how this works in relationship to Rust, right? So yeah, this is all great. We can build UI now. We have a whole bunch of components. We're making components, new components every day now. It's going pretty quickly. But we only have a desktop theme, right? We only have the dark desktop theme right now. We're working on mobile themes and having a much broader set of widgets available that are easily usable. Right now, it's, yeah, you still have to do your own styling. So how does this DSL, how does this UI structure work? How does that work in relationship to Rust, right? Because it's a little bit like an HTML engine in some ways. You know, it's an engine that takes in a structure like let's go back to the very simple, the first application that we made. It's an engine that takes in. Let's run it as well. Simple. There we go. Yeah, it's an engine that takes in this UI structure and generates these graphics, right? So the way it does that is it uses the derive live trait, or yeah, I don't know if anyone knows Rust well enough to know what a derive is, but a derive allows you to write a macro that generates code based on what is written here, what is written after the derive, like a struct or an enum or a type. And it allows you, the idea is in Rust that you can derive traits, and traits are essentially bags of methods that you can call on an object, right? You can define a trait that has a do things method, and if you implement it for a struct, then you have that method on that struct. It's a really neat idea that is very different from how C++ and Java are, for instance, constructed, because it's a much more dynamic way to compose functionality than other languages have. So they've conceived of the idea that you can derive these traits if you can automate them, right? So if I can derive a set of methods, I can write a macro. These are called derive macros. I can make a macro that implements that functionality. And in this case, you see struct app, right? And you see these little things. These are called attributes. So these are attributes. And these attributes mean something to the derive macro, in this case, the live macro. So we have a live attribute, which says, hey, this value actually is read from the DSL, from our custom language. And when you say Rust, it means, yeah, just don't touch it, right? Whatever you do in derive live, leave this value alone. That's what it means. It's just for the Rust side, you put Rust in there. So this is very, very straightforward. So this derive live macro, if anybody knows Serde or serializers in Rust, it is a way to use compile time reflection, and reflection is a way for code to read the structure of data, right? A reflection is a way to read the structure of data and then programmatically do something with it. Like, for instance, generating serializers and deserializers. Because in C++, for instance, generating serializers and deserializers is a terrible problem. Even in JavaScript, it's not great. Like, we have JSON, but if you have any kind of structured data types in there, it is not going to go over well. It is not, but with Rust and traits and derived macros, you can write compile time reflection and serializers. And this is one of the great leaps of Rust that I think is maybe lost on people just starting out or looking at Rust in the beginning. But it allowed Makepad to automate binding this HTML-like language to Rust. So if you look at the implementation of live for widget ref, you will see that it actually contains a little interpreter to deal with this language, right? So every component that you see here is actually its own custom little interpreter for this language. So every node in the tree is given a data structure that represents a key value object, essentially JSON. It's just a JSON object in Rust, conceptually, and it's given that node. So this is why when you see the drawBG having functions like shaders, it's because this implementation of the interpreter on that shader object is actually a compiler for shaders. It's a different context for the language. And that's really nice because that allows me to make a whole lot of very fun widgets, like, for instance, the slide viewer as well, right? Like the slide viewer is a widget that implements, right? So here we have live hook. I said before, live hook allows you to interact with the live trait. Right? The trait is derived, but you still want to provide information or want to do stuff in the flow of that deserialization. And it has a bunch more methods that I'm going to show a few of now. So the first one is before live design. And this is, you see there's no self, so it doesn't have an identity. It is just, hey, do you want to register any components that we need to be aware of? In this case, it registers the widget slide view. That means that if you do this, now the constructor of slides view is known to the generic object like view. So view can now make a slides view. This is just a registration point for a constructor of a component. And then you have before apply. That means, hey, we're going to give you a new DSL structure. Do anything you need to do to clean up or whatever. In this case, I clear the drawing order of the slides. Because the drawing order is provided by the DSL, and if you live code the DSL and you give it new data, you want to reset the draw order because you're going to build it up as it deserializes, right? So you reset it here. And then I have a hook called apply value instance, and if you look at the DSL code for the slides, slides app. If you look at DSL code for the slides, you see that all these slides are in here. They have no name, they have no ID, but they are instances of a slide, right? So there's a whole list of instances of a slide in there. And the default deserializer has a little hook that says, hey, I'm running into an instance and I don't know what to do with it. Do something with it. And in this case, what it does is it actually constructs the slide. So I have a bunch of different points where you can apply, where you can send it new DSL data. One is, for instance, the animate. Right? When I use animation, when you see those values change in the buttons, I do that by generating little fragments of that UI DSL that you send to your object to be deserialized. So giving that structure to your UI allows you essentially in a static language to have dynamic data application, right? So in JavaScript you would just walk over the objects because you can traverse any object from tooling. But in Rust you can't, right? It's a static piece of memory. You cannot reach outside or through it. You have to give it a trait that can reach in. So in this case, the animation engine is actually using the same deserializer or the same application structure as the UI would live code. So live coding and animation engine use the same data path. Yeah, I'm not going to go in too much detail here, but you could do new or update, and then what it does is it actually inserts a new child node based on this thing here. Right, so a slide, once it's through the entire inheritance engine and expands to the final objects, it can be given to a widget ref. This is the apply function that I talked about, where you give it new UI structure, and then it spawns up. So that means that in Makepad, there is no global engine for UI. It's all localized. So every single component can essentially implement its own, entirely own render structure. Like editors could be, use what Eddie just showed you. Slide viewers can use incremental rendering. What is it? Things like the synthesizer are essentially a giant static UI that doesn't change, so that it can use data binding. So Makepad is essentially a multimodal UI framework. It doesn't have a very fixed structure. You can make, depending on the domain of what UI you're building, you can make a domain-specific rendering engine localized to that widget. And we do that all the time. So yeah, I think that is properly in-depth enough in that regard. Let me get back to, oh, my slides are now in here. Let's go to hot loading. Yeah, so the way the hot loading works is essentially the same as using animations. You just send it a new UI structure and you ask the whole UI to update its values based on the new thing. So that's how you get live coding in a statically compiled language. And I alluded a little bit to the widget system, right? So the widget system is, so Makepad has an immediate mode draw architecture. So you begin drawing and you give it all the data for the screen, and then you end it. It's essentially, it's an immediate mode structure. But we also have a retained mode UI structure. So it's a hybrid. So every widget can do immediate mode rendering, but it can itself live in a retained mode structure. And these two are hybridized. And that is, I think, no other UI framework has done that. And I've always wanted it because you want to have both things. You want to have an immediate mode structure for an editor or for lists or data. And you want to have a retained mode structure for when the UI is much more static. Like, for instance, the panel structure of this what is it? The panel structure of this UI is pretty static, right? It's dynamic in the sense that it's mutable, but it is a static structure. I'm not regenerating at every frame, but that little virtual viewport for the text editor, I am. So hybridizing that is key. And so the widgets, when I say our widget system, you should think of that as our retained mode widget tree. Just like a browser has an HTML DOM tree, we have a retained mode widget tree. But you can use the widget tree in any way you want. So if you have the slides, or you have the list view like this thing, if you have the news feed, right? The news feed is scrolling, and here's a button inside an instanced sub-item. You have an outer widget that is inside a retain mode structure, a list box that is inside a retain mode structure, but inside the list is an immediate mode drawn data list, and inside the items are again retained mode UI structure. So this button and these buttons and this layout in the structure is retained mode. So you can hybridize that completely. And that is, yeah, I think that is very different to anything I've seen before, and very valuable. if you go full immediate mode, you run into performance problems and also scalability problems in terms of how to structure your code. It's not very nice. And if you go full retain mode, you limit yourself to what kind of UI you can render. So, and one last little thing I want to show is, so how does Makepad run these applications, right? Like, these are not windows, these are child processes for the IDE. They're running inside the IDE on a texture, and they also resize smoothly, which was actually surprisingly hard. The way we do that is by using a render to texture for a child process. So the process that you see here, it's Ironfish. The application that you see running here is running on a texture. It is not running in a window. It doesn't have a window loop from the operating system. It is using a custom window loop that we made for it, running on standard in this case. And it is only sending a texture to the host process. And that allows us to do something very, very useful, I think, which is make it glitch-free to program. So when you have the news feed, and I change a bit of Rust code here, right? Like I change this little bit of Rust code, you see that it grays out and it comes back, right? It grays out and it comes back. That interaction, if you don't have that process isolation in a child process, you cannot do, because it'll pop up a new window, or it will mess with your UI, or you cannot have the fake live coding as we have it in there. And it also allows me to dog food this application. So for instance, we have Makepad in Makepad, right? Because I have to be able to use Makepad myself to make Makepad, because otherwise it's not a good tool. If I can't use it myself, it's not a good tool. That's my rule for tools. If I'm making a tool and I can't make the tool in it, then the tool is not good enough at making tools. So that's not good. But you know, then you also need to be able to edit the tool in the tool, because otherwise, how are you going to debug editing the tool in the tool? But you know, then you have the problem, of course, like what if you want to debug editing the tool in the tool in the tool, and then you have to go here. So as you can see, we have a fully functional, complete nesting of IDEs. So I think inception has been achieved here, and we have a tool that might actually work this time. So that's my talk. Thank you.